Good morning, everyone. So in the last class, we have seen some of the experimental process and some of the calculation, some of the estimation, and how the different equipment are used in the isotherm test, and how the calculation are being made. What are the different steps? In brief, what we have learned in the last class. Okay. Today, I have discussed up to the calibration of the reference cell and the sample cell, the leak test, and the void volume also. Okay, and I have also discussed with you the example sheet. Okay, the data sheet. This is the data sheet for the reference cell and the sample cell volume calibration. And then I have showed a data of a particular cool isotherm test. This is the sample, and the upper part, this part is for the void volume test. Okay, you can see all the data, all the notes are given here for the conditions and for the sample information and the reference cell and the sample cell. And then the last the last two sections, this is for the adsorption test with methane, and this is the desorption test with the methane. So today we'll be going to discuss about the construction of the adsorption isotherm or the desorption isotherm and some related issues. And then we'll be directly going to the next appendix B, about the error analysis. Okay, these two will be the main discussion for the today, and then it will be over. And at the end of this class, I have to discuss with you about the class test. Okay, because the schedule is been given. You all know about the exam schedule. So I will be discussing with you about the test and about when you will be coming to the campus, and accordingly I'll be putting the viva, because I will not be giving you any assignment this time. So that's why the two class tests will be there, two normal class tests, not the long class test, two normal class tests and one viva. Okay, no assignments will be given to you for my subjects. So is this datasheet visible to all of you? Can anybody please confirm?
Yes, sir.
Okay. So if you have read this appendix and the procedure, okay, I hope you will be able to understand the different process. But then let me explain you. If not, then let me explain you. Let me open the figure. Yeah, this is the experimental setup. Okay, this is the experimental setup, the gas cylinder, the data acquisition system, the data acquisition system here, and it is being displayed here in the monitor. This is the water bath, and into which the constant temperature water is circulated, distilled water is circulated. Okay, and this is and it is the total surrounding or the ambient temperature is regulated by this AC. This is AC controlled room. Okay, otherwise it is not possible to control the surrounding temperature at the 30 degrees centigrade. Okay, and this is the experimental setup we have seen, and we have learned about this in the last class. Now suppose you have seen that before we are going to construct this isotherm, first we have to calibrate, first we have to do this experimental setup, you have to fabricate, then we have to do the leak test. Every time we dismantle or we assemble some part of it, we have to do the leak test every time. Every single time you are taking for the sample, you are opening a valve, not the valve switch, but you are opening the valve from the system or from the assembly. You have to do the leak test. Okay, once you are done with the leak test, and leak test should be performed at the some higher pressure of the maximum absorption pressure. Suppose you are going to conduct the adsorption at pressure up to 8 megapascal, the leak test should be performed at more than 8, 9 or 10. Okay, it should be performed at 9 or 10 megapascal, so that for the total range of the isotherm test, you will ensure that there will be no such leak. Once it is leak proof, then for this test there will be no such leak. Okay. After the leak test, what we are going to do, we are going to use the helium and we are going to calibrate the reference sample part and the sample cell portion. What is the reference sample part? The reference sample part is from this area. Let me enlarge it. from this part, okay, this is total up to this valve. So this total part, if you can see this total part up to this connector, it is the referential part, okay. So which is having 150 cc referential, which is the 50 cc. This is the 50 cc referential solid steel, okay. And there are some fittings, valves and the pipe fittings, and from here this two-way valve to this pressure transducer and the sample cell are the portion of the sample cell part, okay. So these are the references for the sample cell. Now as this is very much difficult to measure for all the moving parts or all the small parts, so what we are going to do, we are going to estimate this by using helium gas. Helium is non-absorbable, okay, and the diameter, the kinetic diameter of the helium gas is 26 nanometer. 26 nanometer. 1 nanometer is equal to 10 to the minus 9 meter. Okay, so this helium can penetrate to very small open volume spaces or the pore volume spaces or any volume spaces, and it can give the idea about the void volume. Now, as you can understand that all the gases, the methane is having a kinetic diameter of 38 nanometer, carbon dioxide having a diameter of 33 nanometer, and krypton, it is also having some higher, maybe 40 nanometer, okay. So all the common adsorbed gases, methane, carbon dioxide, and sometimes nitrogen also, they are having much higher diameter than the helium diameter, okay, because helium is the smallest diameter of 26 nanometer. So helium can access some of the small pore size ranges into that 20 to 26 nanometer or maybe 26 nanometer to 30 nanometer, which may not be accessible for any methane or carbon dioxide particles, gas particles. So what is going to happen? Suppose below 33, carbon dioxide would not be able to access. So it will, whatever it will not able to access, it will consider the total part is the some solid volume. Okay, so there lies the problem. So, but helium, what helium will do? Helium can penetrate to the smallest part according to its smallest diameter, and it will show the maximum amount of the void space into the sample cell, which is higher than the than the than the data of methane and the carbon dioxide, because their diameter is much higher. So they cannot access all the volumes, whereas helium can access more or less all every places, okay, all the places. So that's why sometimes this measurement of the density, the pictometry, the helium pictometry, by which we are going to measure the porosity and the grain density. I hope you all understand what is the grain density. Grain density is different than the bulk density. The grain density is higher, and this is measured by the helium, and that's why sometimes this helium measured density is called the excess density. It is also called the excess density. Why? Because helium can penetrate and it will tend to overestimate the void spaces that may not be accessible for methane and carbon dioxide. That's why it is called the excess density by sending helium gas. Okay. Now, whenever you have measured this void volume, you are going to calibrate this referential and a sample cell. You need to have two equations for two unknown of referential and the sample cell part. Okay. And you have seen earlier that for one part we are not putting anything, we are just taking some of the 5 or 6 uniform pressure steps. Okay. Following the some equation of state. Here we have followed the Span-Wagner equation of state, and we have measured at the Ashram temperature. Here it is 30 degrees centigrade, and the pressure is varying from 0 to 6 megapascal. Okay, generally this is the range of the low to medium pressure adsorption Ashram construction. If it is high pressure, it will become in the range of 8 to 10 megapascal. Okay, so when you are going to put the helium gas at an increasing steps, suppose 1000 then 2000, you will be getting the both the initial gas content, the initial condition, and there will be referential condition, the final condition. So from that you have conducted one ratio, one type of arrangement, and one ratio VR by VS you have got, and next you have opened the sample cell and you have put some of the glass balls with some, before putting the glass balls, you have calculated the number and the total volume that the glass balls they are going to occupy. And then again, you are going to measure the same helium gas. You are going to same using the same Boyle's law for the helium gas expansion, and you are going to get another ratio which is called the VR by Vs minus Vb, where Vb is the ball volumes, okay, glass ball volumes. So you have got this two ratio, and if you are going to interchange this and you are going to arrange, you will be able to solve these two unknown parameter of the VR and Vs from these two equations. So your second step is also done. You have calculated the calibration volume of the reference cell and the sample cell. Now, as I have mentioned, this experimental setup, you can do 30 number of tests or 50 number of tests or whatever number of tests. But if you are not going to change, or you are not going to remove, or you are not going to add any new part of this setup, you need to calibrate this only once for all the 50 or 100 samples. But if you are going to change one two-way valve to a three-way valve, or if you are going to add some extra length of this pipe or any fitting, then again you have to do the calibration for this empty volumes of the reference cell and the sample cell, because the volumes may get changed. So this has to be done only once for only one particular setup, okay? And for rest of the samples, you don't need to measure it. It is only has to be done for the first test. So after this calibration volume, again you are going to open, you are going to take out the sample, you are going to take out the setup, and you are going to open the sample cell, and now you are going to put the cold sample into it. Okay, the cold sample may be dry, it may be wet. There are standards of preparation, okay, of preparation of the dry sample and preparation of the wet sample. Some of the ASTM procedure you may know, because during the preparation of the dry sample or wet sample, wet rock sample, you may have learned some of the ASTM standards, but here also the standard is somewhat different, and it is also available for dry and the wet sample measure preparation technique. Okay, the sample preparation standards are not so important to you, but this is also some idea is just required, and it is given in this text. So please go through the text and you will be able to understand that for preparation of the dry sample or preparation of the wet sample, what are the standards or what are the conditions you need to maintain. So once you are going to put the sample, cold sample into the sample cell, then again you have to do the leak test, because you have opened and now you have to again check for the leak. So leak test generally done for the 24 hours to 48 hours at the highest pressure steps, at the most pressure, a little bit higher pressure than the last adsorption pressure steps. Okay, and after that you are going to start the absorption isotherm. Okay, and before you are going to start the absorption isotherm, you have to again, after leak test, you have to again do the void volume calibration. Okay, the void volume calibration is to be done by this. Okay, the void volume calibration is to be done by by helium expansion, and it will be giving you the ratio like this. Suppose after leak test, you can see you have known the sample cell volume, you have known the reference cell volume. This is the density of the methane. This density of the methane is the sorbed gas density. It is the sorbed gas density, okay? And then this is the weight of the sample you have calculated, and this is the DAF. DAF means minus of ash and the moisture percentage, what is the total weight. Okay, so if you are going to take this weight fraction, everything whatever you have calculated, this will be represented by DAF. Okay, and you can see initial reading has been given. This is the to check what if there is any transducer error when there is no gas. So initial reading is 0, and this is your gauge reading plus initial reading calibration plus your atmospheric pressure will give you the actual this 3504 or all the pressure values. Okay, and you can see that units are also given. Gauge pressures are in kilopascal. Z rho of the gases is taken from the span Wagner software. Okay, this gas row of the gas. That means the gas density are of two types. One is for the soft gas, which is taken from the any journal. This is the for the soft gas density, and one is the free gas density, which is lying in the free part of the sample cell, void volume on the sample cell. Okay, for the soft gas, that density will be given as 0.421 gram per cc, but for the free state gas, methane, that should be calculated at the temperature and the particular pressure. Okay, this ZRI is being calculated again by the software with the Span-Wagner software using the Span-Wagner or equation of state. Okay, and you have to provide the value of the again pressure and the mole fraction and the temperature. Okay, here methane is the only one, so it is mole fraction is 1, so total 100% is the methane. So if you are going to calculate this, you will be getting this equation, you will be getting this ratio, which is the VR by VV. So if you know VR, you will be able to calculate VV, as you can see here. For the sample cell reference cell volume of 64.368 cc, you have calculated void volume as 100.981. Okay, so the coal volume should be sample cell minus this void volume is the coal volume, and with this coal volume we are going to calculate the density as this. You can see that the coal density lying, the powdered coal density is variation of the coal density is only 1.1 to 1.4 gram per cc, but here as you are going to measure it by helium gas and all the coal powders are not of the same fraction. Okay, because you have taken minus 100 to 150 plus size, so the size variation is there, so that's why a little variation is also there. Okay, there is also little variation of the coal density measured. So you can see that some of the ratio are already neglected, which are on the higher side, and most of the ratio which is very much close together we have taken, and it is in the fourth decimal point. You have to consider fourth decimal point, otherwise it is very much sensitive. You have to be very much sure about the void volume, because if there is any error, and you will see that it is one of the most significant parameter which can give error for the measurement or estimation of the gas storage capacity or the gas content. Okay, so you have to be very careful. So once you have calculated the ratio, you are going to calculate the coal density and the coal volume and then what is the total void volume. Okay, now you are going to, after you have done this test, you are going to remove all the gases. Okay, again it should be in the 0-0 condition, all valves should be open to the atmosphere, and imagine that all the systems are in a 0-0 condition. That means all the reference cell and the initial and the sample cell are in 0. Okay, no gases are there. You are about to start the adsorption process. Okay, so here you can see that in this case, okay, this is the seam name is the local 2 seam of Jhoria coalfield, okay, of Jhoria formation. It is having a dry sample and at 30 degrees centigrade. It is at that situated at the depth of 118 meter. Okay, the sample we have collected, it was in the 118 meter of depth. Okay, and then we have started the adsorption, and you can see that approximately we have maintained some equal gas information, equal gas steps. First it is the 1001, and then approximately at 800 to 900 gas steps uniformity we have maintained. Okay, so suppose what we are going to do at the first case. Suppose all the pressure valves are open and we have to see the dash, the data acquisition system is recording the data, so we are going to see that what is whether there is any initial error or not. So from that display in the computer we are going to check the initial reading. Okay, next we are going to inject some of the pressure at the reference cell, but in the sample cell initial, you can see this is only the 101 only the atmospheric pressure. The gauge pressure is 0 because there is no such pressure we are going to allow it. Okay, why this 101 we need to consider? Because we cannot vacuum it. It's nothing, it cannot be vacuumed. Okay, there is obviously some atmospheric pressure is already there. Okay, so that's why we have just taken that there is no gauge pressure. So initial step, the sample cell, there is no air we have assumed, so the gauge pressure is showing 0, but at the atmospheric pressure, whatever pressure it is showing, we have to calculate what is the mole. So accordingly, in the PRI and the PSI, the initial condition of the reference line sample cell, we have calculated ZRI and ZSI, you can see. And then with this, we are going to calculate the mole. How? This is the equation. Mole N is equal to PV/RTZ. Okay, this is the equation. You can see. Okay, N is equal to PV by RTZ. We are going to we are going to take it here. This V will be the referential volume. We are going to put it as 64.368. R, universal gas constant at this value. T is this 303 K absolute temperature, and Z is, again we are going to calculate whatever is Z. So we are going to calculate mole Ri and mole Si. Okay, this is the initial step. Now some amount after the readings are more or less stabilized, suppose after 2 minutes or 3 minutes, if you are going to inject some gas into the reference cell, at some point, depending on the fraction of the second, depending on the compressibility, depending on the temperature variation from the cylinder to the 30 degrees centigrade in the water bath, it will expand, it will contract depending on the pressure and the temperature condition. So we have to give some 2 or 3 minutes, and then we are going to take this reading. Then we are going to open the valve in between. Which valve we are going to open? Let me show you. Okay, and this is the graph we will be getting in the reference line sample cell after opening the valve. Okay, so I'll be showing you this later. If you consider the sample cell, this is the way, this is the connected to the same cylinder, you can see. Okay, the cylinder is going to be connected here. This is the midpoint, cylinder line will be coming, and you are going to put this into the reference cell. So this to this is the total pressure. It is showing as 1100, suppose. And then when it is stabilized, this is showing 0 sample initial, or 101 only total pressure, and this is 1000 plus 101, so 1100 approximately. And then we are going to open this valve. If you are going to open this valve, this middle 2-point valve, some amount of the gas will be going into this cell, and you have to totally open and directly you have to close it within a fraction of a second. Why? Because there is a cold sample into it. So you will see the graph is suddenly it is going to increase, and then it is continuously going to decrease. Okay, the moment you are going to close this valve after opening within a fraction, you will going to see that this reference cell graph will be stable after one time, but sample cell graph is going to decrease. Why? Because coal is there, and as there is some amount of the gas, methane is here, so methane is now being absorbed. So the pressure graph will be seen like this. Reference cell pressure from the 0 means the point when we have just started the injection, okay, into the sample cell. So you can see the reference cell pressure is more or less stable for this 12 hour. For each of the tests we have conducted, we have given 12 hours for equilibrium time, and see this sharp decrease within the first 1 hour. This is for the methane absorption into the coal sample. So you can see how sharply it is going to fail, and all these points are showing you 0. So at the very initial point, within 0 to 10 seconds, it is just going to be very much up, and then it is going to fall. And here also in the reference cell also you can see that it is coming down. Why? Because some amount of the reference cell gas is already transferred into the sample cell. Okay, so this is the type of the graph you are going to get. At the end of the 12 hours, if you see that this line is more or less straight, and you will also see that I have also discussed into this that when you are going to consider the equilibrium, okay, you are going to consider the gases in equilibrium when there is the pressure variation for 1.5 hour or 2 hour is very less. You can see when the pressure variation within the cell become negligible, plus minus 2 kilopascal from any fixed rating for a period of 1.5 to 2 hours. That means suppose at some time the pressure after 1000 pressure, you are going to get a pressure of suppose 400. So if you see that 400 kilopascal is maintained, or only 401 or 402, not more than that, maintained for 2 hours, then you can assume that no further gases will be absorbed, and this pressure state has reached equilibrium. Okay. So what you are going to do then you will be going for the next step. Okay. So you will be at this equilibrium point, you are going to take the pressure reading again. So you can see this is the PRF, final pressure reading of the reference cell, and the PSF, final pressure reading of the sample cell. Okay. This is 414 total pressure and this is 504. So you can see approximately 1100 and 100 was the initial one for reference cell and sample cell respectively, and then it is coming to the 504 and 414. So see, the reference cell pressure is 504, but the sample cell pressure is approximately 100 or 90 kilopascal apart. Okay, otherwise this should have shown the equal pressure if there is no adsorption. But as there is a gas adsorbed in the sample cell, okay, that's why the pressure is always less. So at this pressure also you are going to calculate the mole RF, mole SF, sample cell and the reference cell final. Then what you are going to do, this is one step is done. See the calculation now. Mole sample final, okay, and then mole system initial means ri mole ri and plus mole psi mole si. These are all the initial samples in the reference cell and sample cells. So this is the mole system initial. Then comes the mole system final. Mole system final is the sum of the mole rf and the mole sf. At the final condition, what is the mole fraction? Okay. As the gases are going to be adsorbed, so obviously the simple initial will be higher. So now we are going to subtract sample initial minus sample final. You are going to get mole adsorbed. Now we are going to get some value. Okay. Then this is the mole. Mole is just a number. But now I have to put number of mole per unit weight. Just like the notation, if you remember, that the unit is mentioned for the gas content of the gas storage capacity is the per unit basis or per weight basis, SA per ton or CC per gram. So that's why we are going to convert it mole to millimole. 1 mole is equal to 1000 millimole per gram, dividing by this DAF weight. Okay, so now this is the representative of the DAB basis. So millimole per gram. Now you can see the N Gibbs. This is a new term to you. The Gibbs or the excess absorption, and there is an absolute absorption. Okay, if you read the text carefully, I have discussed that whatever experimental value we are going to collect, these are all termed as the Gibbs or the excess absorption value. Why? Because we are going to neglect the amount of the solved phase gas into the void volume of the sample cell. That means if we are going to consider the sample cell, okay, we are going to calculate the free gas state by taking the total volume of the sample cell minus the cold volume. But some amount of the small gas fraction can be present in an adsorbed state into this void volume that we are going to neglect. As this subtraction, as we have to subtract but we are going to neglect it, so whatever value of the number of the mole adsorbed we are going to estimate, this is the excess one. So that's why it is termed as the excess absorption, or as per the name of the scientific who has hypothesized this, okay, who have suggested that, it's called the Gibbs adsorption. If we are going to consider the soft phase volume also, and we are going to reduce that term from this number of the mole, okay, and so we are going to correcting and we are going to calculate that exact number of the mole considering all of the gas of the state, it will be called as the absolute adsorption. This is given as N abs. You can see this is termed as the last column N abs. Okay. Now, how to calculate this? There are obviously there are laws. Okay, there are the formula. So I'll be discussing with you later. First, from mole adsorbed, then the millimole per gram unit weight, then cumulative. Cumulative means 0 plus 0.1232. Okay, so total at the end of the first step, you are going to get only first step value. At the end of the second step, your stage adsorption is only at that stage, but your cumulative adsorption is first step per second step, total adsorption. So you can see that for all the 6 or 7 stages, 1, 2, 3, 4, 5, 6, 7, there are 7 steps. So for millimole per gram stage adsorption, you can see that all the adsorption are going to reduce, more or less it is going to reduce, and the first one is the maximum one. You can see at this column. Whereas for the cumulative, it is going to increase because it is going to be additive. Okay. Now this cumulative, you are going to change the terms in the cc per gram with some unit transfer. Okay. Cc per gram is the Gibbs adsorption, and then with the soft gas density. Soft gas density is this, and at this pressure temperature we have to collect what is the free gas density of methane. This is the free gas density, and with this Gibbs adsorption, with the equation of the soft gas density and the free gas density, we can calculate the absolute adsorption. So we have calculated cumulative absolute and then the cumulative cc per gram. Okay, so this stage one, okay, this stage graph and the cumulative one, these two are important to us, and we have plotted it like this. You can see there for adsorption there is a two graph. You can see the blue one, the lighter blue with a rhombus type icon, okay, or bullet, it is the stage adsorption graph. You can see this is the graph. Stage adsorption first is the highest, and then it is going to continuously reducing. Why? Because if you are going to think about the total pore space available for adsorption, at the very first step it is 100% available. At the second step, some amount of the gases is already adsorbed, so the total available space is less than that, so it is going to be reduced. At the end of second pressure stage, it will be again somewhat reduced because again some amount of the gases are already stored, okay, are already with them, are already stored into that coal, so less pressure availability, and then so on it is going. So this is the blue stage adsorption graph, and the cumulative one is the square graph. Okay, you can see it is going to be increase, and then as the pressure increases it is going to remain the flatter. Okay, at this highest stage, if it is going to become flatter, this will be termed as the Langmuir volume, but still it is increasing, so you cannot take this volume as the Langmuir volume. You have to calculate. Similarly, after your final adsorption stage is done, you can see at this figure, at this data, at the last final stage of the adsorption, we have reached the sample cell as sample cell pressure as 4602, and so we know at this final step what are the number of the molecules are there. Okay, what is the number of molecule? So these final pressure step molecules should be represented at the first step of the desorption. So see, I have again put it here. This is the final step of the millimole per gram. This is the first step of the desorption. I have started with these two. Okay, and one point you need to see that for the first step, initial point is 0 and the final point is whatever you are getting as 414 and the calculation. When you are going to consider the next step, the next higher step, suppose the second step, you are going to inject some amount of the gas at the uniform gap in the reference cell, but then the sample initial pressure will be not as 0, it will be same as the earlier one, because from where you have stopped in the last step, that is the initial step of the successive steps. So see, the 414 and this all the unit, all this data are again going to be coming here at the initial step and serve as the initial value for the second step. So this is same for all the pressure step, you can see here. Okay, because we are not going to allow any leakage, we are not going to allow any escape of the gas or releasing any gas. So whatever was the final step volume or number of the mole, the same it will be getting into the first step. So this way we are going to conduct the experiment at number of steps. Now this number is totally up to you. Okay, but why I have taken these 7 steps? Because the more number of the point, the more point on the graph, and so the chances of the error will be less. If you are going to take sir only 4800 na, so I can take only 4 points at 1200, so suppose you will be getting a graph like this: 1, then 2, then 3, and then 4. So only 4 points. So if you are going to calculate the error, any substantial error to any one single data point will give you a very higher error into the testing. So that's why the more number of point. Again, you should not take more number of point, not more than 10 or 20. Depending on your highest pressure steps, you can take 7 or 8 pressure steps. That will be sufficient. Okay. But you must take them at uniform gap. What is uniform gap? I am telling. Uniform gap means, see, it is more or less 800 or 700 gap. Okay, that thing you need to constant. Now, once you have got this adsorption done, you are going to start the desorption. How you are going to dissolve the gas? See, this is the initial reading now. And now you are going to take, suppose at the end of the adsorption stage, what is happening? See the sample setup. If all these valves are closed, suppose at the sample's final stage, you are going to be getting some reading, and the difference final step, some amount of the gas will be there, you will be going to read. Okay, this final step is there. Now, this sample final will be the sample initial during the first step of the desorption. Now, for desorption, your pressure has to be reduced. So obviously, sample cell pressure should reduce, otherwise there will be no desorption. But how you are going to reduce the pressure? You have to vent out some amount of the gas. Now you can see here that from the sample cell you cannot vent out any gas because there is a valve and this is directly connected to the reference cell. But from the reference cell you can vent out. If you open this part, you can vent out some amount of the gas from the reference cell to this channel. Okay. So now suppose at the first step of the desorption, you are going to vent out some amount of the gases from the reference cell. So suppose earlier it was 4600 and suppose 5600. Now your reference cell pressure is coming as suppose 500. So it is going to be reduced at some point. After you have stabilized this again after 5 minutes, then you open this middle valve. So now, as some part of the gases are released from the reference cell, obviously there will be some transfer of the gases from the sample cell because there is a void space into the reference cell. So some gas molecule will come, some pressure will be coming to this reference cell. What will happen? The sample cell pressure will come down. Okay, and then the gases will start to dissolve. So if you see the reading again, see the reading 3200, 3206. This was the 4600, 4602. This is the initial. See, I have put this thing in the initial, and then sample initial, I have reference initial, I have put down from 58512 to 3206. I have substantially 1000, approximately 1400. I have put reduced. So now the reference initial is 3200, sample initial 4602. Now you open the valve and see the final stage 4034 and the 4092. So some of the gas pressure is reduced. Okay, gases will be dissolved. Now when you are going to calculate this, your calculation will be sample initial minus sample final. Sorry, sample final minus sample initial. Why? Because in the final case, gases are dissolved. So the gas molecules are higher in the final case, not in the initial case. And so on, you can see that I have done the reduction in the 800 or 700 approximately. Okay, 800 days. But you can see that I have taken 4 pressure steps at the same step. Why? Now let us see the graph. You can see up to 80120, it is coming only 2006 to 1307, 1304. What is 1304? For the adsorption, Astam, see the red one. The desorption graph will always lie above of the adsorption graph. Why? Because the total amount of the gas, what is totally adsorbed, it will not be able to dissolve. The state desorption will always lie below the adsorption graph because at each stage, whatever total adsorption was there, desorption will be much less than that. And the cumulative one, the total desorption cumulative graph will be above of the adsorption graph. Why? Because whatever gas content was there, whatever gas was absorbed, okay, this is going to show you whatever was there and how much is the after desorption. This is the number of dissolved, and after desorption how much is there. As the desorption state desorption is always lower than this state adsorption, the desorption graph, cumulative desorption graph, cannot come down to the cumulative adsorption graph. Why? Let me again repeat you. As the desorption graph, state desorption is always less than the state adsorption. That means at a particular stage, whatever gas is adsorbed, it is much higher than whatever amount of the gases are dissolved because of the residual gas content, because of the some nature of the graph. You can see that depending on isotherm, you have to substantially reduce the pressure to get the production. Okay. So in the first case, you can see this is the final. This is not actually the final pressure. This is after, from this point, after reduction of the desorption pressure, this much only. If you do the scale here, only this small fraction vertical difference between this point and this point is the gases dissolved, which is obviously less than the gases absorbed. So that's why it will still lie above. Okay, whereas if you consider the adsorption stage, the earlier this was the adsorption. So if you consider this here, from this to this is the total amount of the gases absorbed at this stage. Okay, so that's why the desorption graph will lie above. Okay, and see at 1304, this is the 1304. If I have not taken any other pressure step, any other this point, so this was the final adsorption point. Why? You see this 1300 because there was no other pressure to 0, because reference is already at 0. So then what I am going to do, I have taken the same at 0 pressure reading with reference 0. I have taken 3 or 4 readings to get, this is the adsorption. You can see this is the 1304. So I should have taken 1304 at the final one, and then I am just connected with 0, but I will be losing these 2-3 points. So that's why I have to take another 3 point with referential 0 and see, now I am going to get the some 3 points. Okay, so if you are going to see this, so you can see that for adsorption I am going to take 2 point, but for desorption, even if I am going to reduce it, I am not going to get very close related point to the pressure from the initial. That's why during desorption you have to take this into consideration. To get more point, you have to take some pressure steps, some more pressure steps at 0 pressure, and then you are going to get the graph. This is the total connection of the adsorption desorption isotherm, the relation between it, okay, and the total nature of the adsorption of the isotherm. Okay, it is only 10:48, and let's not discuss any new thing today. Okay, let me stop it here. If you are having any question, anybody, you can ask me, or I have to discuss something. I have to talk with you regarding your test. Any question, please ask.
हेलो सर।
Yes.
सर कुछ अलग क्वेश्चन था सर। प्रोजेक्ट इवोल्यूशन के बारे में कुछ पता है, कब तक होगा?
ये तो अभी एक मीटिंग नोटिस आया है ना. आई थिंक यू पीपल नो दैट द डेट इज ऑल्सो गिवन फॉर थर्ड ईयर एंड फॉर फोर्थ ईयर. द डेट इज ऑलरेडी गिवन फॉर प्रोजेक्ट इवोल्यूशन एंड फॉर एग्जाम्स. Circular has come na. I think you have also got the circular. So once you are into the campus, then sequentially this lab, then end-sem exam, I think everything will be as per the schedule. We don't have any chance to do otherwise. Okay. You have been notified by authority na, with some circular. You have
सर
received some mail.
उसमें लिखा है कि 15 मार्च तक सब कुछ वाइंड अप करना है, वाइवा
No,
और
that is for the theory class. That is for the theory class. That is for the theory class. For project also, it is already mentioned that up to May, I think. Up to May, I think, or maybe at the end of the end sem exam only, you will be it will be decided. Okay.
ओके सर.
Okay. So no questions for any classes for class related issues. Again, I can see that some of you have put this on hold. You have put it hold and left the window, I think. Anyway, okay, then let me stop the recording and then I need to discuss with you. Yeah.